Okay, yeah, thank you very much for introduction, and also thank you very much for this great invitation to Sweden. So yeah, today I'm going to talk about my recent work with my great collaborator Si Chen, and he is now just graduating University of Tokyo and will move to University of Minnesota. Yeah, yeah, this one, and it does. Okay, it works. Yeah, so right, and the line of my talk is I'm going to discuss the stability of topological solitons, which is very old problem in condensed matter and high energy physics. And conventionally or traditionally, we have we have known that this kind of stability of topological soliton can be classified using homotopy group, but our finding is this conventional wisdom is not fully correct. So and actually it depends on more delicate algebraic structure if there are non-trivial interaction between interdimensional solitons. And surprisingly, this kind of selection rule or conservation law of topological soliton can be nicely described by non-invertible or categorical symmetry, which is the main stuff of this conference. And the outline of this talk is I will first going to giving an introduction, and next I will discuss about our original finding of this non-trivial behavior in 4D CP1 sigma model, especially about what is called stability of Hoppion. And after giving a detailed explanation of construction of non-invertible symmetry of 4D CP1 sigma model, I will give a brief mention about its mathematical structure behind that is controlling the non-invertible solitonic symmetry. And I will summarize my talk. Yeah. It will. So, yeah, I think first line is okay. In many usual setups, so we can have symmetry controlling the quantum system, and that kind of symmetry Z can be spontaneously broken to its subgroup H. And in this kind of standard setup, if we pay attention to low energy effective theory, we are basically giving an effective action for Namb-Goldstone boson associated with this spontaneous symmetry breaking. And nice description of this effective model for Namb-Goldstone boson can be given by what is called as a coset construction. And we consider a nonlinear sigma field sigma, nonlinear field sigma, which is a mapping from space-time to this target space, G divided by H. And the partition function, or low energy effective partition function, can be given by the path integral for this nonlinear sigma model. And this small fluctuation of sigma nicely describes the Namb-Goldstone boson, and it nicely explains the low energy scattering physics between energy bosons. But there is also a large fluctuation that is not captured by this kind of small Namb-Goldstone boson fluctuation, and those are basically characterized by topological soliton. And depending on the symmetry breaking pattern, we may have this kind of domain wall setup, vortex, or hedgehog, or monopole, etc., depending on dimensions. And our main target is to understand the stability of this kind of topological solitons. And in order to understand this topological stability, key idea what we have developed is a homotopy group according to for example, this kind of old review written by Marmin. And in this case, so we are considering a space mapping sigma. Remember, the sigma is a mapping from space-time to this target space, nonlinear target space G over H. And in order to find a nice topological soliton like this kind of topological soliton should have finite action or energy density. And in order to having this kind of finite action energy density, field configuration on these infinite boundaries should be giving should be point a specific one point direction in the target space. So effectively to describe or classify topological solitons, we can identify these infinity of the space-time as a single point, and you can consider a one point compactification of the space-time. And this kind and solitons are now classified by homotopy or topological stability as a mapping from this sphere to the target space, and naturally homotopy classification of topological soliton arises. And recalling that the conservation law should be related to symmetry according to the philosophy of nature. So we should be able to understand this kind of topological conservation as a symmetry of the sigma model. And actually conventional wisdom, in the conventional wisdom, we are saying that this kind of solitonic symmetry is basically understood as a Pontryagin dual of this homotopy group. And our question or main theme of this talk is whether this conventional wisdom is actually always true or not. And in order to give a interesting and subtle counterexample of this conventional wisdom, first I want to give a detailed explanation about 4D CP1 sigma model. All right. Yeah, and assume that so we are, yeah, for example, we are now having 3+1 dimensional space-time, and the quantum system is living on it. And assume that that quantum system is having SU2 symmetry, and it is spontaneously broken to a U1 subgroup. For example, we are considering a situation like summing a quantum antiferromagnet, which is having a SU2 spin rotation, and it's broken to a specific direction like G direction spin rotation, and unbroken symmetry is just that U1. And then in this kind of situation, so target space of nonlinear sigma model is given by SU2 divided by U1, which is nothing but 2 sphere or CP1 target space. And detailed description of this CP1 is not so important, but in order to give a concrete description, let me take this specific realization of this CP1 sigma model. First, we regard that we are having SU2 valued complex scalar field G, which is, you can regard that this is a two-dimensional complex valued scalar with this unit norm constraint. And in order to express, realize this U1 division of this target space SU2, so I also introduce an auxiliary U1 gauge field and consider this kind of natural minimal coupling gauged action for this complex scalar field. And in this effective action, A is just an auxiliary field, since this is just a quadratic action for A. So you can integrate out A by using the equation of motion, and A can be written as this kind of form using this complex valued scalar field. And this expression turns out to be important for later discussion. And in order to discuss homotopy, in order to describe a topological soliton of this 4D CPR model, homotopy is still important data. So let me remind what is a relevant homotopy group. First, homotopy is trivial, so there is no vortex. So for this CP1 is the same with S2, so pi2 of S2 is integer. So you can have a kind what is called magnetic skyrmion or monopole-like configuration. And the non-trivial fact of this S2 homotopy is pi3 of S2 or CP1 is also integer. And this follows from Hopf fibration, and topological soliton associated with this non-trivial pi3 is often called Hoppion in this context. And before talking about this Hoppion, so let me give a detailed let me give a description of this easier case pi2 of S2 is equal to integer. And in this case, what we have what we call vortex or a monopole soliton. And since pi2 of CP1 is integer, so this suggests that according to the traditional classification of solitons, so we should have a U1 corresponding U1 symmetry. And actually using this kind of field, so we can construct a nice Noether current explaining this conservation law, and this is given by magnetic flux of auxiliary U1 gauge field. And actually, so since this is just a field strength, if you take a derivative, it is just zero, so it is conserved by topological conservation law or Bianchi identity. And since we are now considering 4 dimension, it gives a U1 one-form symmetry. And corresponding charged object in 4D spacetime is given by a 't Hooft line or this kind of line operator. So definition is if you pick up this transverse plane of this line, then this transverse plane is actually a 3D spacetime, and this black line is now becoming a point in this 3D spacetime, so you can surround it by S2. And if you integrate or count the magnetic flux of S2, this should be quantized to integer due to Dirac quantization condition. And this integer Z is nothing but this pi2 of CP1. And let me denote this 't Hooft line or vortex line operator as Vn of L, where n is specifying this integer value n. And we will see that there is actually a final classification of this 't Hooft line or vortex line operator in this 4D CP1 model. But before that, so let me first going to tell about what the hop soliton or hopion is. So next, let me move on to the soliton related to the non-trivial pi3 of CP1. So pi3 of CP1 is integer because of S2 accept this hop vibration, or it is nothing but S3 is SU2 and S1 is U1. So this is actually expressing that S2 can be realized by spontaneous breaking of SU2 symmetry to U1 subgroup. And because of this hop vibration, if you apply homotopy exact sequence, you can find that pi3 of S2 is an integer. And let me construct what is called as a hopion or hop soliton associated with non-trivial pi3 of CP1. And in order to measure pi3 of CP1, so actually we have to give a Noether charge, and actually by following the seminal work of Wilczek and G in 80s, we can give a nice expression for this hop number using the U1 gauge field A. And using auxiliary U1 gauge field, if you consider the Chern-Simons form, which is a 3 form, and if you integrate it over S3, it turns out that it is quantized to pi times integer. And this integer is related to this pi3 of CP1. So if you consider the point-like defect, and if you surround by S3, and if you consider the boundary condition so that this Chern-Simons integral is pi times some integer, then that integer gives a hop number. And here I want to make a remark that generically, if you just consider the Chern-Simons form for general U1 gauge field, this kind of quantization does not occur. But now this U1 gauge field is an auxiliary gauge field given by this constraint. And because of this, so if you consider derivative of this Chern-Simons form, this dA squared turns out to be 0 because the target space is just a two-dimensional sphere, but 4 form living on two-dimensional sphere is 0. And because of that, this Chern-Simons form is now topologically conserved. And we can see that this is a quantized number. So we can now characterize this integer as a Noether charge given by this integration formula. But unlike the case of pi2 of CP1 case, integrand of this hop number is not a gauge invariant quantity. So although this homotopy class, if you're just looking at the third homotopy of CP1, so we would like to judge that this 4D CP1 sigma model has a U1 zero form symmetry, but do we accept U1 symmetry without having net current? And more subtlety, so more non-trivial subtlety appears if we consider the vortex soliton related to this hop number. So let me go back to the definition of the vortex operator introduced in two slides before. So I just introduced the vortex soliton as just a top fifth line of U1 gauge field, and this N is giving a magnetic charge. But if you go really consider the serious definition of this kind of line operator, you have to remove the infinitesimal neighboring boundary of this line operator, and it now becomes this kind of donut. And you have to specify the boundary condition of CP1 valued sigma model field on the boundary of this torus. And you should define what is a good vortex operator is by classifying the topology of the boundary condition of this CP1 sigma model field. And this N is always is well defined even in this more detailed definition, because if we consider this orange circle, this is actually an S2, and if you measure a magnetic flux on this S2, it is always an integer. But actually, if you consider the homotopy of mapping from S2 times S2 times S1 to CP1, then we are having a more detailed classification of this vortex operator. And in particular, to understand the presence of the final classification, we can ask what is a possible, so this S2 times S1 is also a three-dimensional manifold. So you can now ask what is a possible value of hop number of this on this S2 times S1. And if you can define this hop number, this topological vortex operator should be classified this magnetic charge N and also this hop number on S2 times S1, which is written as K. And the point is this K accepts G2N classification when N is a non-trivial integer. And in order to see it, let's try to evaluate the hop number on this S2 times S1, given this formula. And although this seems to be well defined as an integer, but this is actually not, because if we consider the U1 large gauge transformation along this S1 direction, then this Chern-Simons integral gets this extra contribution because of this large gauge transformation. And because this is large gauge transformation, so integration of this epsilon gauge parameter along this S1 is 2 pi quantized. And this dA S2 integration of this magnetic flux is now said to be N for this vortex operator. So this hop number is ambiguous under gauge transformation, and it can be shifted by 2n times integer. So point is, so this hop number on this S2 times S1 is not a well-defined quantity as an integer, but it is well-defined in G2n. And actually, it is known that if we consider the homotopy classification from S2 times S1 to CP1 sigma model or S2, so this problem is solved by Pontryagin, and it is he shows that so it is classified by summation of G2n with non-trivial with magnetic flux n. So this is a field theoretic or quantum field theoretical reinterpretation of the old work by Pontryagin Thom construction. So now we would like to understand what is the actual symmetry related to Hoppian or related to pi3 of CP1. And if we evaluate local correlation function in a compact space time, and if we put several solitonic defects, then it turns out that this kind of correlation function can be non-zero only if total Hoppian charge is equal to 0. This is basically saying that we are having the U1 conservation law. However, so this is not totally correct if we consider the mixed correlator having both topological, both Hoppian defect and also the vortex line defect. If we consider this kind of correlation function, this can be non-zero only if summation of this local Hoppian charge plus this Hoppian charge of line operator is 0 in modulo to n, this can be non-zero. But if it is non-zero, if it is non-zero in modulo to n, this has to vanish. So basically, this is saying that under the presence of line operator, this U1 conservation law is reduced to this G2n conservation law. Yep.
So shouldn't there be also like a one-form symmetry conservation law, which tells you that if you insert only one V, you get 0?
So now we are considering a compact spacetime with closed line operator. So this is 0 in whole spacetime. So that one form charge is 0 in whole spacetime.
Okay.
Basically, because line operator is putting particle and anti-particle for one form charge. Yeah. Oh, but so for example, if we having a compact spacetime like torus, and if this line operator is wrapping along a non-trivial cycle, actually that kind of constraint appears, as you said. Yeah.
So you consider S3 and S2 times S1. What about other manifolds like T3? Do we also need to consider them?
Yeah, so there is actually a non-trivial constraint in such a kind of situation, but it turns out that this is giving us sufficient detailed data. So here I will not consider it. Yeah. Okay. So now we are seeing that without line operator, Hoppian number conserves as a U1 symmetry, but under the presence of line or most severe situations, that conservation law reduces to G2. So does this suggest that the symmetry group is U1 or G2 or completely something else? And the answer is completely something else. And I believe all participants attending this conference is familiar with this generalized notion of the symmetry. And currently, we are believing that our motto is we are having generalized symmetry as long as we are having well-defined topological operator, and non-trivial commutation relation with topological operator can give an interesting conservation law, as in the case of usual Netter's theorem. And in usual continuous symmetry, just integrating this Netter charge on closed manifold gives this kind of topological operator. And the topologicalness of this Netter charge is equivalent to the usual differential version of the Ward-Takahashi identity. But we can now consider more general kind of more non-trivial general fusion rule like non-invertible symmetry. And in 2D, it is well controlled by fusion category symmetry under some reasonable assumption of finiteness, etc. And we are now we are having much endeavors to generalize this kind of extension to higher dimension or more general case of non-invertible symmetry. And so point is, in order to construct a generalized symmetry, we would like to construct topological operators. And how can we construct topological operator? And you can construct topological operator using the help of topological quantum field theories. So in order to find this kind of unconventional symmetries, a useful recipe developed by these guys is that, so first, prepare a topological quantum field theory and couple our sigma model of dynamical field in a topological way to this TQFT. Then because of this, because TQFT is of course topological and we are only considering a topological coupling, in this way we can construct a topological defect operator for this dynamical field in a non-trivial way. And in this way, so it is very manifests that everything is topological, and what we should check is if this kind of topological operator actually acts non-trivially on local operators in dynamical quantum field theories. Yep.
As you said, sometimes the fields of the bulk theory that you couple on the defect are dynamical. So is it obvious that the defect that you get is topological even when they are dynamical?
So in order to ensure it, we only consider topological coupling.
Okay, the coupling is topological, but the field itself is dynamical in the bulk.
Yeah,
so in the bulk, you are integrating over, in the path integral in the bulk, you are integrating over all dynamical configuration of the fields. So
right, that's true.
It's an assumption, so
So at
it's
least
not obvious.
for this case, this recipe works well to construct the topological defect operators. Yeah. Okay. So in our case, what we do is we first prepare level n U1 Chern-Simons theory like this. That is living only on a codimension 1 surface, and we construct a Hoppian symmetry generator in this way as a partition function of this level n U1 Chern-Simons field, and it has a topological coupling to the CP1 sigma model, and this A is an auxiliary field of the CP1 sigma model. And let me now check how this Hoppian operator is, this Hoppian symmetry generator acts on this kind of Hoppian defect operator and also on vortex operators.
So I guess you can also construct all the rational numbers, no, like this. So
Right, exactly. So here, for simplicity, I'm considering the basic ingredient, but of course we can consider more general minimal DQFTs. Yeah, of course. Okay, so let me act Hoppian symmetry generator to this point like Hoppian defect. So in this case, so we are just considering, so our manifold surrounding this Hoppian defect is just S3, and on S3, so U1 gauge field has no non-trivial topology. So you can just integrate out in a naive way. So for example, in order to perform the evaluation of this Hoppian symmetry generator, so you can now just consider the naive completion of the square, and because U1 bundle is trivial, so this kind of naive operation is totally fine. And we will see that, so you just have a 2 pi over 2n rotation with this Hoppian charge. So if we consider this kind of correlation function when S3 is surrounding this X, then it just gives this kind of phase factor which is just a G2n rotation of this Hoppian symmetry, giving the Hoppian charge K. So we can see that this Hoppian symmetry generator correctly detects the Hoppian charge of K. And since this capital N can be an arbitrary integer, so basically, so by considering the whole set of Hoppian symmetry generator for each integer n, then this kind of correlation function has an ability to determine this K as an integer. So basically this recovers a U1-like selection rule for point like Hoppian defect. And what is more non-trivial is the action of Hoppian symmetry generator to the vortex line operator. And in this case, in order to surround the vortex line operator, so we have to consider defining submanifold of this Chern-Simons partition function as a S2 times S1. And we would like to evaluate this Hoppian value of the Hoppian operator, Hoppian symmetry generator on this vortex line defect. And now, since S2 times S1 has a non-trivial topology, so integration of this U1 gauge field should take into account the contribution of the non-trivial U1 bundle. And basically, it is saying that so this S2 times S1 basically, so integration of this Chern-Simons form of B field on S2 times S1 is basically coming from non-trivial holonomy of this B field. So integration of S1 over B is written as beta here. And magnetic flux of this, yeah, some chat is up. Yeah. Question?
Question?
Okay, please speak up.
Can you hear me well?
Yeah, I can hear.
Hi, just a question on the previous slide. So you said that this action determines the charge as an integer. But thinking back to Pavel's talk, last week, does it determine the charge as an integer or as a profinite integer?
Prefinite integer. So sorry, I do not know what the prefinite integer is. So
okay.
yeah, so sorry. Yeah. So yeah, let's chat later after my talk. Yeah, I'm also interested in what you and me. Okay. So let's go back to the evaluation of this Hoppian symmetry on this vortex. So integration. So contribution of the non-trivial U1 bundle of S2 times S1 is basically summarized as the integration of the B field holonomy along this S1 and also summation over all possible monopole charge on S2 for B field. So basically it contains this kind of form. And because of this BDA topological coupling for this sigma model field, it also gives a contribution of beta times n, where n is a magnetic flux of CP1 sigma model field. And basically this beta integration saying that so unless this coefficient is 0, so this integration is 0. And point is for B field, so we are summing up all possible magnetic flux, but it is should be an integer multiple of capital N. So only when this capital N divides this small n, which is a magnetic flux of CP1 sigma model field, this contribution of the path integral can be non-zero. And in particular, so if this capital N is equal to this small n magnetic flux, it captures, so this Hoppian symmetry generator captures the Hoppian charge K in modulo to n correctly. While if n is not a divisor, because there is no corresponding m making this contribution to be non-zero, so this Hoppian symmetry generator turns out to be non-zero. So if we so in one way to regard this, so let's see. So we would like to give a naive integration over B fields, then we would like to reproduce a Hoppian symmetry, Hoppian charge in this way. But when manifold is non-trivial, this Hoppian charge is gauge dependent up to modulo 2n or something. And only when this rotation angle eliminate that large gauge ambiguity coming from large gauge transformation, you can get a non-zero meaningful value. While when it is gauge dependent, it just becomes zero. And in this way, this Hoppian symmetry generator acts non-trivially, and when it fits a periodicity of G2n, and this recovers a G2n selection rule under the presence of vortex defect operator. So summary for CP1 sigma model is Hoppian symmetry associated to pi3 of CP1, which is equal to integer, is neither U1 nor G2. And actually, correct symmetry generator is given by this kind of TQFT partition function, and the fusion rule would be much more complicated because it should be controlled by those of 3D TQFTs. And when vortex operator is absent, basically this is saying that U1 symmetry can be recovered by this considering this kind of symmetry generator. But when vortex operator exists, then U1 symmetry is effectively reduced to G2n kind of symmetry according to this symmetry generator. And we can also find that G2 subgroup for fermionic case is a good invertible symmetry given by this kind of thing. And in that case, that is controlled by spin Bordism group. Yep.
Why this Bordism group is spin?
Yeah, so it depends on whether you consider this 4D sigma model as a spin QFT or a bosonic QFT. And if you just consider it as a bosonic QFT, this should be just usual homology. And in that case, there is no interesting non-invertible subpart.
But so the problem is that the Scherz-Simons term is a spin Scherz-Simons term.
Yeah, right.
Okay.
So when we consider 4D CP1 sigma model as a ferromagnetic QFT, then yeah, this Chern-Simons level can be odd. But if we regard 4D CP1 sigma model as a bosonic case, then that Chern-Simons level also has to be integer, even integer. So
Okay.
Yeah. So spin structure of QFT also affects the possible level of this Chern-Simons.
So for example, if you consider it as a bosonic theory, you could also have the possibility of putting the theory on a non-spin manifold. In that case, you would not see even the Z2 selection rule.
Right.
Okay.
That's our, yeah, exactly. Yep.
Okay.
Yeah.
And sorry, I have also another question, because previously you showed that the U1 selection rules are violated in general in presence of vortices.
Yeah.
So
right.
if you claim that the symmetry is large, I mean the only conservation law which is always true is the Z2 one. I mean non-spin manifold. So if you claim that the symmetry is larger, how do you see explicitly by manipulation with topological operators that even if you have a topological operator, this does not imply a selection rule in general?
Let's see. Yeah. Let's see. So yeah. Well.
I think the problem is the presence of the vortices.
Yeah, so basically, so it is just saying that, so if we consider this kind of topological defect, and if you just moving it, and when the vortex is, when vortex is present, then even if you surround for just a 3 sphere, but when you need to surround this vortex, you have to consider the non-trivial topology contribution. And in that case, so we try to consider larger symmetry than G2N, then when acting this Hoppian symmetry generator on this vortex, it just 0. So correlation function with the net charge just becomes 0, and basically it doesn't tell anything. So in that way, so when capital N is fit into this G2N conservation law, so you can get a non-trivial selection rule, meaningful selection rule by considering this kind of correlation function, including net charge defect operator. But if we try to consider larger U1, then basically, under the presence of net charge, this correlation function just vanishes and nothing can be told. Yeah.
Thanks.
Yep.
Okay, so we continue with the questions. Okay, so so I also had 2, right? So I did 2, and okay. So what? I will be quick. So maybe can you go back one slide, please?
One slide.
Thanks.
Okay.
So one way to understand this selection rule, no? Can I think of this as your non-invertible defect mapping this V line? How did you call it? Monopole line. This monopole line into a twisted sector, no?
Yeah, maybe.
And then
yes.
it becomes a tadpole when you
Yeah. I think so. Yeah.
Okay. Then a second question, which is also quick. Can you consider some kind of UV completion of this model, like QED theory?
Yeah, that's a very interesting question. And honest answer is I do not know. But as you said, so this kind of symmetry generator is almost same with ABJ anomaly symmetry generator. So I think there could be a UV completion using that one.
Yeah, I think that what happens at the Toft line as a chiral charge. This is the
I think that is UV meaning, but I haven't tried to make this story complete UV complete, so I'm not sure honestly, but I believe that that is the case. Yeah.
Okay, thanks.
Okay. So this is the end of section 2. So I want to briefly talk about the mathematical formulation behind this solitonic symmetry. And our proposal is still a tentative one, and I do not yet know we do not yet know the full story, but I want to still give a tentative proposal for general structure behind this solitonic symmetry. So what we are interested in is we are considering this kind of sigma model partition function, and when we have this kind of path integral, what is a topological, what is a general symmetry generators controlling the topological soliton related to this target space. And here, so as a technical remark, here this target space Y can be infinite dimensional formally. For example, it can be a classifying space, for example, in order to include the presence of a situation in the presence of higher gauge fields. But here, we would like to put another different type of finiteness assumption for a good controllability of the later discussion. Although I'm not talking about the details of our construction, but as a technical remark, so we are assuming that so all the homotopy group are finite, and also for a sufficiently large degree, homotopies are vanishing. And so in this case, so for example, when Y is S2, so there are infinitely many non-zero homotopies. So this kind of assumption is correct, strictly speaking, does not hold. But when we are considering, for example, D-dimensional spacetime, important information of this kind of topological soliton only uses a homotopy up to D degrees. So in that kind of situation, so we are replacing Y is by its postonic truncation to satisfy the second constraint. So this is a technical remark, and maybe so in future development there could be a more better formulation that does not need this kind of finiteness assumption, but for a moment we are assuming this kind of technical assumption. And when we having topological soliton, and when we would like to discuss solitonic symmetry, corresponding symmetry generator should be a topological function depending on the sigma model field. And furthermore, we would like to, and for this kind of topological function, we would like to assume the presence of a notion of locality. And with this kind of requirement of locality give us very strong constraint. And it is natural to assume that that kind of local topological function should be given by some kind of partition function of TQFT coupled to this sigma with target space Y. And in order to treat it mathematically, so this kind of locality constraint, locality condition naturally arises if we consider a fully extended TQFT. So we are regarding that those topological functional for sigma can be written as a partition function of fully extended TQFT. And in order to take into account the information of target space Y, so this TQFT should be Y enriched one. And here, so maybe many of you, so let me explain what this fully extended means. So these fully extended TQFTs are the mathematical formulation of TQFTs extended Attia's action of TQFT to include locality by Dolan, and especially nice work by Jacob Rulli. And in original proposal of Attia, so basically partition topological field theory is regarded as a symmetric monoidal functor from Bordism category to vector space category. And here, so important restriction of this vortex Bordism category is, for example, if we consider D-dimensional Bordism category, so we are just considering closed D manifold or D manifold with D-1 dimensional boundary, and we can we can glue them to consider the play the game of Bordism. But the point is we cannot consider more lower dimensional defect in this formalism, and important development by considering fully extended one from ATIA is that partition topological field theory is now understood as a Bordism n category to some target n category, and in this case, so for example, Bordism n category is basically understood as for when Q is less than n, then Q morphism are regarded as Q manifold with boundary or also with corners. And basically, because of considering the higher category, so this allows us to cut manifold into into many small pieces, and in that way, so because you can cut manifold into very small pieces, so every information of TQFT can be put into a local information. And especially considering the fully extended version allows us to formulate the cobordism hypothesis proposed by Stolan and proved by Jacob Lurie in a suitable version of Bordism category, saying that fully extended TQFT itself is having a one-to-one correspondence to the fully dualizable object of the target category. And the idea is any manifold can be constructed. So for example, even if you consider a non-trivial manifold, you can cut it into small pieces. And then eventually, so any manifold can be constructed by gluing this very small object in the vicinity of the point. And since higher category allows us to glue them in a non-trivial way, so if you evaluate just a partition function of this small point, in a small neighborhood of point, and that takes a value in the fully dualizable object of the target category. Then if having this information, then whole data of TQFT can be just reconstructed by gluing them. And so all the non-trivial data of TQFT is now summarized into this local data. So in that way, so fully extended version of TQFT realizes this topological quantum field theory in a quite local way. And we follow this idea to classify a solitonic symmetry generator. So first, let us define why enriched TQFTs following this idea. So first, we consider n-dimensional fully extended Y-enriched TQFT are given by given by symmetric monoidal functor from Y-enriched n-Bordism to target n category. And here, following the proposal by Gaiotto and Theo Johnson-Freud, so we take a specific target n category given by repeated Karoubi completion of vector category. And honestly, I do not have a good understanding of what this Karoubi completion is, but basically, so it is giving a minimal extension of a vector category, keeping every things fully dualizable or finite dimensional. So this is one of the nice minimal option to consider it as a target category. And in this talk I do not use detailed knowledge of this one, but I just say that we consider Y-TQFT given by this definition. And according to cobordism hypothesis, this symmetric monoidal functor can be equivalent, can be replaced by equivalent data using the point evaluation or partition function on a point. And then, so now it can be considered as a functor from target space Y to this target category sigma n-1 to the back one. And we call this functor as an n representation associated with this TQFTZ. TQFTZ. And here, so when we say this Z underbar as a functor, Y is also regarded, target space Y is also regarded as a category, and that identification done by its identification of this target space Y with its homotopy infinity time, and it eventually becomes infinity group. So it's a invertible version of infinity categories. So it is meaningful to say that this G underbar is a functor, and this D underbar is obtained by point evaluation of G. So according to cobordism hypothesis, these two are completely equivalent. And now topological function of Y should be given by this data G bar. So basically, all possible topological functions should be described by set of functor from Y to Calovi completion of vector category, and we consider it as a we denote it a representation of Y, and this representation of Y is very similar to a kind of cohomology, while it is no longer abelian or having a ring-like structure, but it is a certain type of cohomology, extended version of cohomology, so we call it as a solitonic cohomology. And actually, as an invertible subpart of this representation, solitonic cohomology, for example, in bosonic case, we can claim that this lip Y contains singular homology with coefficient C, invertible C. Indeed, this says that as a subpart, it reproduces a well-known net charges related to Y, and this lip Y now has a non-trivial TQ, has an information of non-trivial TQFT partition function. So we believe that this is a good candidate to characterize a mathematical structure behind the solitonic cohomology. So I think I still have a time, but yep. Okay, sure.
I don't think I understand how you get to this box. So the cobordism hypothesis with this Y structure, where all the bordisms come with maps into Y, says that you take fully dualizable objects and then take a certain homotopy fixed point, so a certain co-limit.
Yeah.
And so it looks so easy. So I don't understand this step, and I'd also like to hear how you connect this to what you did previously, how you actually get the structure. For example, if Y was the classifying space of SO, then there should be trivializations of the Serre automorphism, for example. I don't see how it's in the box.
I see. Yeah. So here, we just believe that this kind of cobordism hypothesis nicely extends to this Y-enriched case. So maybe there is a subtlety in a precise mathematical formulation. So here, we are not completely sure about it, but we are expecting that some analog of cobordism hypothesis should also work in this Y-enriched case, and we are assuming that these two are equivalent. Yeah.
Thank you.
Yeah.
Not going to work, literally, I think, unless Y has finite homotopy groups. When Y has infinite homotopy groups, you're not going to get a fully defined.
But here we are assuming.
Okay, so then you're good. And in that case, there is actually a procedure that computes what you wrote there, sort of essentially by moving up the homotopy groups. It's by iterated cross products.
Okay.
And then this can be made precise with a fairly general target. You don't have to commit to that one. So I think it's
yeah, that's a good news. But yeah.
That's all. Yes.
Yeah. Thank you very much.
Wrote something 15 years ago, paper with my Jacob Lurie and Dan Fried. We wrote the procedure, but we didn't prove that the cobordism hypothesis in this context. We didn't prove that it gives a functor on the whole category, but the procedure is the obvious one, basically. So,
yeah. But extension to infinite homotopy is also very desirable, but here we are assuming everything finite. Okay. Okay, so let me summarize my talk. So we have seen that topological conservation law for soliton is not necessarily fully characterized by homotopy in certain situations, and especially we are seeing this situation in an explicit example of 4D CP1 sigma model. And when for pi2 of CP1, so we have a well-defined U1 one-form symmetry, and we can easily construct the net current. But for pi3 of CP1, so we do not have a good U1. So we can write down the Hopf number, but it cannot be written in a gauge invariant way for general 3 manifold. So U1 symmetry becomes subtle, and actually in looking at this kind of mixed correlator between point-like defect with line-like defect, we can see that this symmetry selection rule can be reduced depending on the monopole number of line operator. And good resolution, it turns out to be given by 3D TQFT partition function, Chern-Simons partition function coupled to CP1 sigma model. And this nicely describes the selection rule for this kind of mixed kind of correlator. And we can see that because symmetry generator are now given by 3D TQFT partition function, so we are seeing that solitonic symmetry also becomes non-invertible or categorical. And in order to understand the mathematical structure behind this non-invertible solitonic symmetry, we are proposing the solitonic cohomology using the cobordism hypothesis, and this would be a good candidate for the mathematical formulation behind solitonic symmetry. So that's everything. Thank you very much for your attention.
So do you expect all of this solitonic symmetry to be some kind of emergent symmetry in the infrared of the sigma model, or you expect that it remains there in the UV completion? Because these guys are heavy in some sense, no?
Yeah, right. So yeah, so at least for this kind, yeah. So as I said, I did not yet try, but I expect this non-invertible symmetry for the CP sigma model can be UV completed in QFT as a ABJ anomalous U1 ABJ anomalous QED plus some sigma scalar field, etc., etc. So I expect some part of this, and I also see that this kind of since solitonic symmetry is basically given by topological function, they are completely commuting. So within solitonic symmetry, so there is no soft anomaly. So it seems that there is no obstruction for possibility of UV completion at this moment. But the honest answer is I do not know. Yeah.
Okay, thanks.
Comment? Or can you hear me?
Yeah, I can hear.
Hi, thanks. That was wonderful. Just to follow up on the math questions. So I think the n vector spaces of Gaiotto, Gaiotto, Johnson, Freyd. I think they're capturing TQFTs that admit a gapped boundary, or they arise via Turayev-Vero construction. So
I see.
I think it's likely that they're not going to capture the kind of topological defects that you get by adding Chern-Simons.
I see.
Theories.
I didn't notice it. Yeah, thank you for saying me. Yeah. So is there a good some? Can I ask? Is there any good replacement to include Chern-Simons, for example?
Yes, I think Konstantin could probably tell you.
Oh, I see. Yeah. That's also a good news. Yeah, thank you very much. Yeah.
Sorry, a naive question. So you mentioned soliton cohomology in an invertible part. Is there a notion of quotienting out by the invertible part? And is it I don't know, this space looks kind of unwieldy, but if you quotient by this, is it
easier to look at? See. Yeah, I do not know. Yeah.
So you mentioned it doesn't have a ring structure or anything like this, or so I cannot quotient, or I can?
Let's see. Other spectra, you mean? Yeah, I think it's possible as a spec. Yeah. Yeah, but yeah, I do not know. So yeah, let's discuss later. Yeah.
Thanks. I also wanted to ask about the target. So in 2 dimensions, there are twisted sigma models, and it's known that they do not extend to the point if you take higher vector spaces as here as the target. But at least in the B-twisted sigma model, it's fairly well understood what the 2 category is that it takes values in. I don't know what it would be in 4 dimensions, but yeah, so the question to you and maybe Konstantin is if you have a guess or know what in general the correct or a good choice of target for sigma models is.
Yeah, I do not know so many.
I don't think on dimension higher than 3 we have a very clear understanding of what a derived version of this would be, because that's what you're talking about. This is meant to generalize semi-simple things, and whereas you're asking about generalized derived categories, higher categories, I don't think we have enough experience with that. You can make some guesses. So if Y, for example, is not has infinite homotopy groups, you can still quantize it all the way to the top, so to speak, to the place where you'd like to get numbers. You won't be able to get numbers because you get infinite vector spaces, but you can do something using chains on Y, at least rational homotopy. But there are several inequivalent things you can construct. So I personally don't have a good understanding of which would be the good one that would cover all the interesting physics applications. So sorry, took a very long time to say I don't know.
So there was a paper by Shuheng Xiao and others on not like selection rules and like interpreting the pion decay as like a non-invertible symmetry matching condition. Would this also live to that? Like, can we interpret like the non-invertible solitonic symmetry as matching some UV non-invertible symmetry instead of having like a pion decay term instead?
So as I say, so just within this topological function or solitonic symmetry, we do not have a Tofuft anomaly. But combined with some electric symmetry, sometimes we could have a Tofuft anomaly related, mixed Tofuft anomaly involving this kind of topological solitonic symmetry. And in that situation, I believe answer is yes. Although I have not investigated some that situation well. Yeah. Yeah, thank you very much.